If you're anything like me, you're deeply concerned with the question of whether any four corners of an n-dimensional hypercube which lie on the same plane can be connected by 6 lines of the same color. Thankfully, you don't have to worry, because as of 47 years ago, the answer is partially yes, provided the number of dimensions is smaller than a number which is larger than the observable universe. Hi guys, I'm Richard Various, and this is episode 6 of Various Things. This is a weekly short format podcast about anything and everything. This week, we'll take a brief look at Graham's number, one of the largest numbers ever used in a mathematical proof. It's so big that if you tried to memorize each digit in Graham's number, your head would collapse and form a black hole before you were done, because a black hole stores less information than what's contained in Graham's number. But what use is a number so big that it would kill you if you tried to memorize it? Imagine you're hosting a dinner party and you've invited 5 other people, so there are 6 of you in total. You want to make sure that you have a good mix of people, so you invite some people that don't know each other and some people that do. Now imagine the seating plan for the dinner table, which looks like a circle with 6 equally spaced dots around the outside, one for each guest. Imagine that guests who know each other are connected by a blue line and guests who don't know each other are connected by a red line. If you're inviting a mix of people, the diagram might look a bit messy, with red lines and blue lines running everywhere. However, if you looked closely enough, you'd find a triangle made up of the same coloured lines, meaning that there would be at least 3 people in this group who were connected in the same way, either as total strangers to each other or as friends. In this example, we can say that if you were looking for a group of 3 people who had this relationship, either all friends or all strangers, you'd need a network of at least 6 people as a prerequisite. Another way of saying this is to say that the Ramsey number for this scenario is 6. If you were looking for a similar network of 4 strangers and 4 friends, the Ramsey number would be 18, meaning that you'd need a network of at least 18 people as a prerequisite. This kind of problem is known as Ramsey Theory, after the 20th century mathematician Frank Ramsey. One of the problems of Ramsey Theory is that numbers grow very large very quickly. To find 3 friends or 3 strangers in a network of 6 people, there are only 8 possible ways to colour our triangle, 2 of which are what we're looking for, all red or all blue. But to find 4 friends in a network of 18, something like a square instead of a triangle, we're looking at 64 possible ways to colour the square, only 2 of which are what we want, all red or all blue. Mathematicians believe that to find 5 strangers or friends, you'd need a network somewhere between 43 and 49 people. So why so vague? Surely 5 is one more than 4, so it shouldn't be too hard, given that there are only 64 ways of colouring a square in a network of 18 people. The thing is, to find 5 friends in a network of between 43 to 49 people, a network with 903 intersections, there would be 2 to the 903rd power possible colourings, which is more possible colourings than there are atoms in the observable universe. So mathematicians talk about a range when they talk about finding 5 friends or 5 strangers, because they aren't able to prove the minimum number of people needed for this to be the case. The calculation would be too large for our current technology to undertake. So numbers in Ramsey Theory are big, but why is Graham's number the biggest of them all? Let's go back to our dinner party example. Remember the seating plan, with your guests sitting around a table with lines running diagonally across? Instead of imagining your guests sitting around a 2-dimensional circle, imagine them sitting on the corners of a cube, but not just any cube, a special kind of cube that can exist across multiple dimensions, something mathematicians call a hypercube. This makes things both more interesting and more complex than just a circle or a square or a pentagon. In the 1970s, a mathematician named Ronald Graham tried to figure out how many dimensions a hypercube had to have in order for a single slice of that cube to be the same colour across all of its edges. So if trying to find 5 friends or 5 strangers in just 2 dimensions would take more numbers than there are atoms in the universe, you can imagine that when we try to find 4 friends or 4 strangers across higher dimensions, the numbers become ridiculously big. So this is exactly what Graham found in 1971 when he published the largest number ever used in a mathematical proof at the time. Graham argued that his number guaranteed that a slice of a hypercube would have all of its edges the same colour for its particular dimension. We know a little bit about Graham's number from his own work and the work of subsequent mathematicians in his field. We know that Graham's number is a multiple of 3, and we know that the last digit is a 7. If we were being cynical, we could say that Graham's number would allow us to plan an interdimensional dinner party using a guest list that had more information than a black hole. But Ramsey Theory, and Graham's work on it, has been used to solve problems in communication, information retrieval and decision-making, all areas of concern in computer science, communication and game theory to name just a few. I've always been fascinated by really large numbers and their applications. We use some of the largest numbers ever discovered in cryptography, for instance, to make sure that nobody can steal our passwords. Astrophysicists use large numbers to describe the origins and ultimate ends of our universe, and to predict astronomical events with astonishing accuracy. I'm keen to know what you think about this week's episode and whether you have a favourite number, so let me know in the comments. My favourite is something called the Erdős number, but we'll talk more about that in a later episode. There's a wealth of resources and further reading for this week's episode as well, so I'll include links to all the references I've used in the show notes on our Patreon page. If you've enjoyed this week's episode and you want to support the podcast, you should check it out. There are great rewards for patrons, like access to exclusive content, extended patron-only episodes and more, and you can support the podcast from as little as $2 a month. You can find us at patreon.com/various things. So until next time, this is Richard Various, and this has been Various Things. Bye for now.